In this video, I'm going to revisit the evaluation of the convolution kernel for the force-damped harmonic oscillator problem. This problem, we have a second-order differential equation, second derivative with respect to x, or second derivative with respect to time of x plus 2 gamma x prime plus omega naught squared x equals f of t. We found that this has a solution, a general solution of the following form. We add up, take the superposition of two solutions of the homogeneous equation, and we add in the convolution of the Fourier kernel for the equation above. We convolve g with f of t and have the general solution. So you would have to plug in your boundary value conditions to make this entirely appropriate. That's a exercise for another time. The specific form of the homogeneous solutions that we found was a damping term e to the minus gamma t times the sine of alpha t and e to the minus alpha t times cosine of alpha t. Equivalent form would have been e to the minus gamma t times plus e to the plus or minus I alpha t. You could use whatever form is convenient for your particular boundary value conditions. And in this case, alpha is the square root of omega naught squared minus gamma squared. Our convolution kernel that we found through Fourier transform methods was minus 1 over 2 pi e to the minus I kt, integrating with respect to k over k minus k1 and k minus k2. And k1 was alpha minus I gamma, and k2 was minus alpha minus I gamma. We have both of the poles of this particular integrand in the bottom half plane. So alpha e to the minus I gamma, there's k1 and k2. What we want to do is we want to evaluate this integral and put it into a more workable form, especially if we're convolving with a complicated or potentially complicated function f of t. We don't want to have to deal with double integrals, and let's see how we can reduce this particular mess of an equation. I needed a refresher on how to evaluate a complex integral. Here's my recap for those who are similarly forgetful of how we go about doing this. The basic idea is that should we want to integrate over some closed curve any analytic function, f of z dz, that is going to be 0. So it doesn't matter what the closed curve is. You want it to be smoother connected closed curve than the one I just drew there, or something else. Any of these will be 0. And in fact, that provided the function f of z is analytic over that entire path, or any of the paths that you choose, you end up with a 0. One easy way to kind of not prove to yourself that this is true, but demonstrate that it's true, is imagine you have some arbitrary complex path, and you deform that path by breaking it. As you come along here, break that path, come on down, and then choose a different path here, and come on back infinitesimally close the other way around so that you come back around. So your integral, presuming you're still integrating around a analytic domain. So we have a contribution to the integral from this portion, this downwards portion of the path, but that's going to be exactly canceled out by the contribution coming back up, infinitesimally close to that on the other side. And then you have here inside a secondary path. Now you can imagine that this was a circle, for example, of radius r. So if you have the integral over this one path C1, and then you have an integral over this opposite oriented path C2, they have to exactly cancel out. So let's perform this integral over this path C2 and see what we get. So if we do that, let's suppose that this point here is S. So Z equals S plus R e to the I theta, and over theta is in 0 to 2 pi. So that is going to be, we can rewrite our integral now in terms of this parameterization. So f of z dz, and dz is going to be r I e to the I theta d theta. Now, suppose you made this circle so small that f of z is essentially constant, assuming it's well behaved over that domain. So in that case, we can pull f of z out of here. So we just have f of s and r I e to the I theta d theta between 0 and 2 pi. And what do we have here? We have e to the I theta over I between 0 and 2 pi, which is 1 minus 1 over I, which is 0. So 0. So our integral over C2 is 0, and our integral over C1 is minus the integral over C2. So it shows us the integral over C1. The integral over C1 also, despite the arbitrary nature of that path, is also 0. That's kind of the basic idea behind complex integration. With the next thing is, how do we deal with a function that is not analytic? So suppose we have instead f of z dz over z minus s. F of z over z minus s is not analytic, even if f of z is analytic in all places. So if we want to integrate that over a path, then what do we do? So this combination, f of z over z minus s, so presuming f of z is analytic everywhere in the integration range, then this is a function that's analytic everywhere except at the point S. So if this is our point S, and we take some path that does not surround S, then f of z over z minus s is analytic everywhere over that curve. So that integral will be 0. If we take some other path that doesn't surround S, we'll get 0. So we get 0. However, if we take any path and this path does surround S, now we don't know what it is. It's not necessarily 0 because f of z over z minus s is not analytic everywhere in this region. It's analytic over this path, but we previously used the assumption that we could deform our path anywhere, and if we deform our path surrounding this little point here, where the function is non-analytic, then we don't know what we're in for. So let's suppose that we deform this integral by, we're coming along here, and we come down, we surround S with a circle, and come back along here, and now continue our path. So if that is our contour, original contour C1 here, and we have a new contour C2, which is a perfect circular contour just surrounding our point of non-analyticity. And we have these two little fragments where we've come down that perfectly cancel each other out. So now our new path is basically of this kind of form. So we have something so we roughly have a curve of this form. And now this happens to be it does not, this entire curve no longer surrounds any points that are non-analytic, and so that one is 0. Then we can say that the integral around C1 is minus the integral around C2. And let's evaluate the integral around C2 just to see how we do, what we get. So if that is our point S, so Z, that's the point S, and our circle around that curve is going to be, C equals S plus R e to the plus R e to the I theta. And now we want to integrate f of z dz over z minus s. And we're coming along here. In this particular case, we're coming along in a negative sense. So we could say that coming over a clockwise oriented circle in this particular case. And so what do we have? We have theta goes from 2 pi to 0, f of s plus r e to the I theta, and dz is ri e to the I theta, d theta, and z minus s is r e to the I theta. Our r's cancel out, our e to the I thetas cancel out, and let's presume that we want to make our r infinitesimally small. If we do that, we make r infinitesimally small, then in the limit, being very non-rigorous, this becomes f of s times I d theta between minus 2 pi and 0, 2 pi and 0, sorry. And what do we have? We have minus 2 pi I f of s. And had we picked a integral that had the opposite orientation, so this is our integral over C2, so our integral over C1 is 2 pi f of s. That's the integral over C1 of f of c dz and z minus s. Where we have picked a counterclockwise orientation. So that is how the result that we get when we integrate a function that, let's say we had a function like f of z equals 1 over z. So something like that. Here s equals 0. Then our result is just going to be 2 pi I. So the next thing we want to understand how to deal with is, what about a function like our convolution kernel that has multiple points of non-analyticity? Our convolution kernel had 2 such points. So it was g of z was minus 1 over 2 pi of e to the minus I k t dk of k minus k1 times k minus k2. And we are integrating from minus infinity to infinity. Now let's suppose that we wanted to extend that integral. We go from minus infinity to infinity, but then we come back around a big giant infinite semicircle. Or we do a similar integral from minus infinity to infinity, and then come back around this way in a big giant integral. So in this way, so we're surrounding 2 of our poles. We have k1 and k2, and in this way, we're surrounding none of our poles. Now, if it should happen that the contributions of this integral of the contour here of this upper infinite circular arc and the contributions of this lower infinite circular arc, if those are 0 under any circumstances, then we can use the entire circular integral in order to evaluate the real axis integral that we're interested in. So in particular, in this case, suppose that we deform our contours. We come along down here and circle back around, come back, and then when we get over here, come along towards our pole, and we circle around, we come back. So we have the integral part. We're interested in this part of the integral, I, that's the portion from minus infinity to infinity, and we're going to hope that everywhere along the circular contour, let's call this C1, that integral is going to be 0, and we know how to integrate along a counterclockwise oriented. We know how to integrate around a counterclockwise oriented circle around our pole, and we have to do the same thing over here. So this entire integral, if we should be lucky enough that this arc is 0, is just going to be the integral around these 2 poles. And that's what we have to do. So when we are integrating around this k1 pole, then e to the I kt over k minus k2 is an analytic function. But when we're integrating around this k2 pole, then e to the I kt over k minus k1 is an analytic function. And we basically just have to evaluate these 2 respective analytic functions at the opposite poles, and we're done, provided the semicircular arcs in the upper and lower half plane are 0. So we're going to have to figure out when these are 0, because they will be in some circumstances, and it will be dependent on t. So let's go ahead and first figure out when we get zeros along these arcs. So if we were on the upper half plane, let's say here, we say z equals k e to the I theta, where theta is going from 0 to pi. And then down here, we have the same thing, c equals k e to the I theta, but theta goes from 0 to minus pi. Yeah. All right, so let's plug in our parameterizations and see when this integral vanishes for what values of t. So in the upper half plane, where theta is going from 0 to pi, we have e to the minus I k e to the I theta, which is cos theta plus I sine theta t, all over k minus k1, which is so k is, or z in this case, which is big K e to the I theta minus k1 times big K e to the I theta minus k2. So this is our integrand for either case. But in the upper half plane, when theta is between 0 and pi, then what do we have in the numerator? So in the numerator, we have e to the minus I k cos theta times e to the minus I times I, which is plus 1. So e to the k, and there's a t here that I missed. E to the k sine theta t. And then sine theta, between 0 and pi, is strictly positive. So this is going to completely blow up unless we need to be infinite unless t is less than 0. And then on the opposite case, when theta is between 0 and minus pi, or between minus pi and 0, I guess we would say 0 and minus pi. Regardless of the orientation of that integral in the range between 0 and minus pi, here sine theta is less than 0 always, less than or equal to 0, so that we have e to the minus I k cos theta t e to the, so we have sine theta less than 0, so we have k something less than or equal to 0 and t. So this will now blow up if t is positive, and so we need t to, this will be blow up if t is negative. So for any, this is infinite unless t is greater than 0. So if we're looking at our contours, we can perform this integral and get some value. Well, we'll get 0, and we require, between 0 and pi, we require t less than 0, but then when we're doing our integral, on the poles, we require t to be greater than 0 here. And now there is a lemma. So this other beastie here, e to the minus ik cos theta t, we have k going to infinity, and we have like an infinite oscillation here, multiplied by a function that's analytic. Well, the function that's analytic is this part divided by what amounts to big K squared. And you could say that with big K going to 0 and this part not going to 0, then you could roughly estimate that you might be able to bound things. I'm not sure, but there is a lemma called Jordan's lemma that basically says if you have this kind of infinite oscillation times an analytic function that is well behaved, so it will, yeah, so we have like a e to the minus something big t and times an infinitely oscillating term, and Jordan's lemma tells us that that entire integral in that limit of k going off to k going off to infinity is going to be 0. Justifying that is a little more difficult. I'm not going to try to attempt it here. So, having found that our integral here along this path is 0, and our integral along this path is 0, we now know that if we choose to extend our integral so that we are in the upper half plane of this sort with t less than 0, then 0 plus 0 equals 0, and we know that our integral in that case equals 0. Whereas our integral here in the lower half plane for t greater than 0 is just going to be the contributions from our two poles. So we're going to want the contribution from our k1 pole, and we're going to want the contribution from our k2 pole, and the orientation of those integrals will be counterclockwise. So we're going to have a plus 2 pi I times what we call the residue for those two poles, for each of those two poles. So let's summarize what we have so far. So our upper infinite half plane integral is 0. So we say that g of t and 0 when t is less than 0. So g of t for t less than 0 equals 0. And that is messy, but gives you the idea. Now we want to do our integral for the lower half plane. We have 0 along these portions of the path. We have canceled segments along these portions of the path, and we have our integral that we're interested in. So our integral will be the negative of our integrals around these poles. So we call this C1, C2, and I. We have I plus C1 plus C2 equals 0. So I is going to be minus the integral around C1 minus the integral around C2. So around C1 minus 2 pi times the integral of e to the minus I k t dk k minus k2. There's our analytic function around k1 divided by k minus k1. So that is minus 1 over 2 pi times e to the minus I k1 t divided by k1 minus k2. And then our integral around c2 is minus 1 over 2 pi, that's 2, e to the minus I k2t divided by k2 minus k1. So we have to evaluate what is k2 minus k1, or k1 minus k2. Let's try k2 minus k1. k2 minus k1 is k1 was alpha minus I gamma. K2 is minus alpha minus I gamma. So K2 minus K1 is the minus I gammas are going to cancel. K2 minus K1 is going to be minus 2 alpha. All right. So we've got lots of minuses involved here and lots of factors of 2. And I've also missed we should also pick up a 2 pi I, a 2 pi I here. All right. So our integral, provided that t is greater than 0, is 2 pi I, and so we're going to have, we have minus, we want minus, and we have a minus in the denominator, so we have minus all told, divided by 2 pi of e to the minus I k 2t 2 alpha plus e to the minus pi k1t 2 alpha. So this is minus c1 minus c2, and there should be a minus sign on this one, if I got it all right. So k1 minus k2 is 2 alpha, and that means that we have a minus and a plus. Plus is minus times minus. All right, we're good. So we have minus I, which is 1 over I, and we factor out the 2, and e to the minus I k2t gives us some, so e to the minus I k2 is going to give us a I times I is minus, let me write it out, minus I k2 equals minus I times minus alpha minus I gamma, which is minus minus is plus. We have I alpha minus minus is plus, but I squared is minus with minus gamma. Minus I k1 is be minus I times plus alpha minus I gamma, which is minus I alpha minus gamma. Good. All right. So that's our side calculation. And go back and plug that in. So we have a minus gamma t in both cases. We can factor out e to the minus gamma t. And we have a e to the I alpha t, e to the I alpha t minus e to the minus I alpha t. And what do you know? We have a sign. So e to the minus gamma t sine alpha t. And I lost the alpha. There was a 2 alpha and 2 alpha. So that is all divided by alpha. And we can now write that our convolution kernel, g of t, is theta of t e to the minus gamma t sine alpha t over alpha. And theta of t is 0 everywhere for t less than 0 and 1 everywhere else. This is our theta of t. And that gives us the constraint of 0 for t less than 0, but non-zero for t greater than 0. And we're kind of in a no man's land at t equals 0. We won't worry about that just yet. So that is our end result. This is the convolution kernel that we arrived at by Fourier transforming our differential equation, finding out what the inverse Fourier transform was of the difference. So we now have our end desired result, and we want to also show that this satisfies the Green's function criteria, and so that if we had introduced a differential operator, the second derivative plus 2 gamma d dt, pen malfunction there. There's a little button on this pen. If you press that button, things just go insane. I don't know what the function of that button is, other than to mess up what you're doing. So if we have a differential operator, L, then we can have L x of t, oops, that is writing behind my image, I believe. Lx of t equals f of t is that's our equation. We want to show that L, if we operate on g of t minus t prime, then we get delta of t minus t prime. That is what would justify calling g a Green's function for this differential equation. Right now, we know that it's a convolution kernel for the equation. So our solution, which incidentally, if you notice, this was one of our homogeneous equation solutions, what we called g of t up above. So our final form of the final solution is a g of t plus b h of t, where g and h have the same structure other than sine and cosine, plus g of t minus t prime f of t prime dt prime. So that's our full solution, and g of t equals theta of t, g of t, which has an interesting interesting that our Green's function, or what we're presuming is our Green's function to be shown, has the same, there's just a Heaviside theta weighted homogeneous solution to the equation. And it wouldn't work with, or at least I don't think it would work if we identified, if we swap G for H in this case. We need G going to 0 at t equals 0, and which is what we have in this particular case. Anyways, next time we will show that G of t is in fact a Green's function, satisfying this relationship, and we have derived a compact representation for that presumed Green's function in this video.